All right, howdy ho, calculus students. I'm not sure why I said howdy ho. I think I'm running out of greetings. At least it's better than my boring greeting. Hello, how are you? I don't know. I have to work on an intro. That'll be my new thing for the future. Get a little intro going. Don't have one. All I got is hi. So we're going to go with that for the rest of this year, which is almost over. This is our last topic on vector valued functions. We're going to touch on polar coordinates and things, and then we'll be done. Almost there. Hang in there, guys. 4 days to go. 4. Okay. We're going to talk about velocity and acceleration associated with vector value functions. That's all. And velocity and acceleration was just like regular functions, pretty much. Let's assume we've got a position function by r. We're going to call it r. And of course, r is going to be your x value and your y value. All right? So we're given r of t. That's our position vector. So what's the velocity? Well, the velocity is just like the velocity of position in a regular function. It's just its derivative. So the derivative of the x component, derivative of the y component, velocity. Acceleration, again, the same thing, the derivative of velocity or the second derivative of position. And that's what we got. All right, now the speed. Obviously, speed and velocity are related to each other. Remember, speed has no direction. Speed is a positive answer. We don't care what direction is. So if you really think about it, in a vector valued function, the speed is just the magnitude of the velocity. That's it. The actual length of the velocity vector is the speed. And of course, velocity is the derivative of the position. Or put into xy terms, it's like the distance formula. It's the square root of the change of x prime of t squared, added to the change in y. Just like distance formula. And that is your speed. All right, let's use it. I'm given this as my position function, and I'm going to find 3 things. I'm going to find, number 1, the velocity vector at 1. So the velocity vector, first of all, is the derivative, which would be 1 negative 2t. If I evaluate that at 1, I get 1 negative 2. There's my velocity vector. My acceleration vector, let's go just t at first, would be the derivative of velocity. So derivative of 1 is 0. Derivative of negative 2t is negative 2. Don't technically have to plug anything in, because a of 1 would be 0, negative 2. In fact, the acceleration is always 0, negative 2. This thing is always being pulled down. Okay, it's not being pulled left or right at all, but it's being pulled down. All right, thirdly, what is our speed? Well, remember, our speed is like the distance formula. How do x's change and y change? And we're given it right here. At 1, our x value changes by a component of 1. Our y value changes by 2. So it's the square root of 5. 1 plus 4. That's the speed at time equals 1. Now I want to graph this. The easiest way I think to graph this is, let's find its rectangular equation. It's a very basic one, because x equals t. We know that y equals negative t squared plus 4. So we do a little substitution. We get negative x squared plus 4. Good old parabola. The vertex at 0, 4. And then if we go either side, at 1 it goes to 1, 3. And negative 1 it goes to negative 1, 3. At 2, we get 0. And at 3, we get negative 9 plus 4, which is negative 5. 1, 2, 3, 4, 5. And the same thing over here. There is our graph. Oh, I missed. I knew I would. Still working on it. But again, I anticipated this problem. So, you remember our answers here. Because what we're going to do, you know what, I'm going to take them. I'm going to take them with me. Alright, we're going to put on this window where I have a nice beautiful graph from Desmos. So that's the graph of R. Now which direction does it go? Well, if you think about it, we know that R of 0 would be, what, 0, 4? And R of 1 would be 1, 3. So we know it has to go this way. Alright, because we know it's going from 0, 4 to 1, 3. Now 1, 3 is important because this is our position at t equals 1. From there, from that point 1, 3, because it's R of 1, I'm going to graph V of 1 and A of 1. Now it's a vector. So if I graph the vector, remember, what color should we make it? Well, we make these a little greenish color there. Okay. So that vector for the velocity is 1, negative 2. So I'm starting there. So I'm going to go over 1 and down 2. So there's my velocity vector. And because it's my velocity vector, it should be tangent. And I think you can see that if we extended that line, it would be tangent. Okay. Now the acceleration vector, we'll give it this color. So the acceleration vector is 0, negative 2. So the acceleration vector would look just like that. Alright, so there's your graph of the position and your graph of the velocity and acceleration all happening when t equals 1. Alright, if you think about it, it's a parabola. Right? Parabola is in motion that way. It's always being pulled down. Always being pulled down. Okay. Alright. Displacement versus total distance. Now we got a couple other formulas for you. So we're going to do the displacement. So displacement would be an integral. Because remember, if you have velocity, then you can find distance and displacement. So it's the integral of the velocity that gives you the displacement. And of course, that would be just broken up into its components. It would be a to b of the x component, and from a to b of the y component of velocity. I'm sorry, so I should say x prime, because it'd be of the velocity of x and y. Alright. Now the total distance. Again, the total distance is the absolute value kind of a displacement. It's you know, if I started here and I walked to the store and I walked back, my displacement was 0 because I ended up in the same spot I started with. But the distance would be how much I traveled to the store and doubled, because there and back. So the total distance is actually going to be the integral of its magnitude. Alright. And we can write it like this, because remember, what is the magnitude of v, or it's the speed of v? So it's just this again. It's the change in x squared plus the change in y squared, this time integrated from a to b. That's your total distance formula and your displacement formula. Let's use them. Okay, we are given a velocity vector, and we're given the initial position of 1, 2 at t equals 0. Okay. What's the position of the particle at 3? All right, so the position would be where it went in its travels from 0 to 3. So it's going to be 0 to 3 of the x component, which is 2t plus 1. But it starts at 1. When t equals 0, it starts at 1. So be careful of that. And the same thing from the y component. Where did it go from 0 to 3? And the y is 5. Remember, the y starts at 2. So this solution would be its position at 3. So we'll do a little calculations here. We end up with t squared plus t from 0 to 3 plus 1, and 5t from 0 to 3 plus 2. Alright, let's see. So plug in 3, we get 9. 9 plus 3 is 12. 12 minus 0 is 12, so 13. 5 times 3 is 15. 15 plus 2 is 17. Alright, there's your position. Now the distance traveled would be the magnitude of that. So we're just going to take our 2t plus 1, because that's our velocity, squared, plus 5 squared. Evaluate that at from 0 to 3. And you get the answer that's approximately 19.650. That's the total distance traveled. And what is that position vector? Well, the position vector would be the antiderivative. Okay? So if we take the antiderivative, what we would get is, let's see, so, well, it's right here, so t squared plus t plus some constant, and the x component would be 5t, I'm sorry, the y component would be 5t plus another constant. Well, just to make it easier, since they gave us time equals 0, so if I plug in 0 for t, I get 0 plus 0 plus c1, so c1 should equal 1. And plugging in 2 when t equals 0, so 5 times 0 is 0, so c2 would have to equal 2. And there you have it. Alright. Alright. Just for fun, I like to check to make sure it works. If I plug in 3 for this, I should end up with 13, 17. So plug in 3 to 5t plus 2. 5 times 3 is 15, plus 2 is 17. Good. Plug in 3 for this, I get 9 plus 12, which is, 9 plus 3, which is 12. 12 plus 1 is 13. Awesome. Alright. 2 more problems, and then we'll be done. If I'm given the acceleration, and I'm given values for the vector, for the velocity at 0 and the position at 0, what are my functions? And what's the position at 2? Okay, so I know if I have velocity, if I was given acceleration, it has to be the antiderivative. So this would be 1/2 t squared plus some constant, and 1/2 t squared plus some other constant. Again, luckily, they give us v of 0. So at time 0, this should be at 3. So very conveniently, thank you, book. I got these right from the book. That's 3. Same thing here. When t is 0, the position should be 1. Makes that constant equal to 1. Excellent. Okay, so there's our velocity vector. Alright, so our position vector would be the antiderivative of velocity. Oh, here we go. We got to do 1/6 t cubed plus 3t plus a constant again. Let's call it 1. And 1/6 t cubed plus t plus a constant. Again, very nicely, they told us the constant at time equals 0. 0, 0, c sub 1 should equal 1. Same thing here. 0, 0, c sub 2 should equal 5. That was very nice. So that would be your position function. And then the question is, what's position at 2? So you just plug 2 into this baby right here, and I'm not going to do all the math. You got to trust me on this one. You get 25/3 when you plug in 2. 8/6 plus 6 plus 1. This would be 8/6 plus 2 plus 5. All right. Cool. Last one. It's broken up in a couple parts, though. Okay. So in this one, we are looking at disposition function. Question is the particle moving to the left or to the right? Left and right is your x component. We really only care about the x component. So is the particle moving to the left or the right? Well, first you need velocity. Velocity is positive, it's moving to the right. If it's negative, it's moving to the left. Again, I only really care about the x component. So this is 3t minus 12t. I'm sorry, 3t squared. So if I plug in 2, I get 12 minus 24. I get negative 12. That means the particle is moving to the left. All right. Good. So I'll fix that one because I didn't write that really well. Now the entire velocity, we'd have to do the entire derivative, which is no big deal. The velocity would equal 3t squared minus 12t is your x component, and your y component would be negative 2t plus 8. We'll plug in the value of 2 and end up with negative 12, 4. So there's your velocity vector at 2. What time or times is the particle at rest? Remember, particle at rest when the velocity equals 0. So let's take our x component. Well, actually, we have our velocity, right? Which was 3t squared minus 12t and negative 2t plus 8. Okay, let's start with this one first. We want to know when that equals 0. I would get, what would I get there? I would get, oh, a t is left. T minus 4 equals 0. Sorry, can't multiply. Which leads me to the conclusion that I have two possibilities, t equals 0 or t equals 4. And now I'll take this one. Set it to go to 0. Well, there's only one possibility there, t equals 4. So guess what? The only time that the particle at rest is when t equals 4, because that's the only time when both the x and the y components have a velocity of 0. And lastly, the total distance traveled. Well, we're given the velocity. So we're going to go from 0 to 4. And we're just going to take the velocity. Remember, this is the change in x. We're going to square it. And then the change in y is negative 2t plus 8. We're going to square it. Integrate that with respect to t. Now we're just going to plug in the calculator. You get about 37.580. All right, ladies and gentlemen, that is the end of vector-valued functions. So I hope you saw they're very similar to regular functions as far as their calculus goes. But in how they deal with an equation, remember, it's an equation where time is a factor. Time makes a difference. All right, so hope you have a great day, and I will see you soon.